is the second part of your momentum, impulse, and collision notes. And on this part, we're going to pretty much just concentrate on impulse and how forces interact in here with impulse, i.e. the impulse-momentum theorem. Okay, so the first thing we want to know is a change in momentum takes what? There should be two factors that are going to change the momentum of this object, the ability to continue doing what it's doing. It's kind of similar to inertia, right? Okay, so the two factors that you want to concentrate on here are force and time. Think about this, a toy truck and a dump truck, right? They're both trucks, it's just one is completely more massive than the other one. So they're traveling at the same velocity. During the same time interval, which would take more force to stop, and why? So stop and think about that for a second. Which would take more force to stop, and why? Well, you don't know what the force is on this, right? But think about what I was just saying. One is more massive than the other one, so mass times acceleration is force. So you have to break down that original equation of F net equals ma net from our previous topic. And from that, if you know that there's more, acceleration is constant, right? Technically it's zero because it's moving at a constant velocity. Okay, so your A is knocked out, which means that you have F equals m. Well, if you have F equals m, that would be a direct relationship. Agreed? So since F equals m, the more massive you are, the more force it would take to stop you, right? Okay, so the less massive you are, the less force it would take to stop you. Imagine putting your hand in front of a dump truck and trying to stop it, and putting your hand in front of a toy truck and trying to stop it. Which would take more force and why? So that's exactly the analogy that I want you to be thinking about here with this. So it all boils down to you have to build upon your previous chapter here, or previous topic, in order to be successful with the next one, i.e. force isn't known, but mass is known, and in order to solve for force, you need to know F net equals ma net, whereas a net is 0 due to being traveled at a constant velocity. Therefore, F equals m actually states that as mass increases, force also increases due to their direct relationship. So therefore, during the same time interval, which would take more force to stop? The dump truck. And why? Kind of going to go a little nuts here on you. F net equals ma net, whereas a net is 0 because they're traveling at the same velocity. Therefore, acceleration equals 0 meters per second squared. Agreed? Okay, so then that would mean that F and A are a direct relationship. Since F and A are a direct relationship, the more massive the object is, the more force it would take to stop it. So therefore, the dump truck, because the dump truck is more massive, i.e. more force, would be needed, applied in the opposite direction of travel to stop this dump truck. Okay, next one, impulse-momentum theorem. Let's put this guy over here. All right, so the equation that I'd like you to think about with the impulse-momentum theorem is going to be that the change in momentum, once again, it's a lowercase p. Capital P is power, lowercase p is momentum. Please use them correctly. It's going to equal force times the change in time. So breaking it down, delta P stands for change in momentum. And F stands for force. And delta T stands for change in time. Okay, time is measured in seconds. Force is really in Newton, but we don't want derived units. That's just too freaking simple, right? So we don't want newtons. We want kilograms times meters per second squared. Yes, yes. Kilograms times meters per second squared. Okay, guys, think about this. If you have a kilogram times a meter times a second to the negative second times a second, that cancels one of them out. So you're left with kilograms times meters times seconds to the negative first. It's kilograms times meters per second. It's the velocity and the mass again. So right there is your proof on how this is really this. Wow, stays the same. Okay, so kilogram meters per second are still the correct units that you would want to apply to a final answer or a given or an unknown for your change of momentum. Okay, so what part of the equation is the impulse part? This is what I want you to do. I'm trying to get you to look at the title right here. Okay? The title says Impulse Momentum Theorem. You know what momentum is, right? What variable is momentum, guys? Please say it out loud. What variable is momentum? Yeah, technically change in momentum, delta P. Okay, so what part is impulse? What variables would you have to take into consideration to be able to appropriately solve for the impulse portion of the impulse momentum theorem equation? It would have to be force times the change in time. Therefore, the impulse is more so known as meters per second squared times seconds. So, in other words, velocity. Okay, what does impulse mean? Impulse means that it is the product of force and the time over which the force acts on an object. It is the product of force and the amount of time over which the force acts on the object. Okay, this theorem means a small force acting for a long time. Stop and think about this in your head. Don't just read it, please, because you're not going to get it if you just read it. Stop and think about this. So picture a small force, like the toy truck. Okay, a small force acting for a long time can produce the same change in momentum as, and I know that's cutting it off from the screen here, but the bottom line there says same change in momentum as. What do you think? What would be the right answer there? So a small force for a long time would be the same as a large force in a short amount of time. Why, guys? Why? Why would you say that a large force in a short amount of time is the same thing as a small force in a large amount of time? Because force and time are indirectly related as long as momentum is held constant. Yeah. Force and change in time are going to be indirectly related together when compared to each other, I guess I should say. When the change in momentum is considered constant, you have to have a constant in each of your equations. So in this analogy here, this bottom line, what this means, this theorem means, is that as the change in momentum stays constant, it does not change, it's not really considered. As your force increases, your time decreases. As your force decreases, your time increases. So a little bit of force, long amount of time. A lot of force, a short amount of time. So think about your hand trying to stop that dump truck versus a whatever, like a cement truck, like stopping that dump truck. It's definitely going to be more forceful, so it should take at least a lesser amount of time to make that dump truck come to rest. So a small force acting for a long time can produce the same momentum as a large force in a short amount of time. So let me just kind of throw that in there. Large force, short amount of time. Okay, next. So here's two analogies. You're driving in your car, right? Someone jets out in front of you. Yeah, it's a crosswalk, but you have the green light, so you slam on your brakes. Are you applying a little bit of force or a lot of force? Seriously. Okay, so you slam on your brakes. You're applying a lot of force. Does it take you a long time to stop? No, you're going to stop like almost immediately. So that would be a large force, short amount of time. Whereas a football player trying to tackle another football player, it's going to take a longer amount of time because they're not applying a lot of force to them, right? Now, if you run into them and tackle them and make them fall over, that's a completely different story. That would be a lot of force in a short amount of time. But in this scenario here in the bottom right, it would obviously be a longer amount of time. Okay, so sample problem, force and impulse. Let's see what we have here. Please write your givens the way that you see them. Okay, so the first that we see is a car, and this car has a mass of 1,400 kilograms. It's moving westward. Masses are not negative. You can't have a negative mass. You'd be like floating around, right? So the mass isn't what's negative. It's the velocity that's going to be negative. So VI is going to be a negative 15 meters per second, collides with the utility pole and is brought to rest, final velocity, 0 meters per second, and a time time of 0.30 seconds. Okay, calculate the force right? We don't want to use newtons, correct? Because you don't want derived units. So kilograms times meters per second squared. Find the force exerted on the car during the collision. So what is the original equation here? Check out what you have. You have a change in velocity here, right? And a final minus an initial. Well, a final minus an initial over time gives you acceleration. So really you're looking at F net equals ma net, but technically that's your original equation, correct? No, that is not your original equation. Your original equation is the impulse momentum theorem. Delta P equals F times T. And then underneath F, you got to do ma net. And then underneath a net, it's Vf minus Vi over delta T. And then you can finally plug in. You have to show the breakdown of all these things. Guys, it's so totally important that you understand that you can show me, you can show anyone, you can remind yourself when you get to undergrad, right, that this is how you solve through this problem. You can't just like start wherever you choose, right? You got to start with the original equation. And on this problem here, it's dealing with force and impulse. So the original equation is delta P equals F times delta T. Now force is what you're trying to solve for. So delta P over delta T equals F. Agreed? Okay, so since you have that, then what you want to look at is your delta P. Your delta P is really, say it, what is your original equation for delta P? Your original equation for delta P is M times your V here over delta T. So that would be MVF minus MVI all over delta T equals F. Maybe you see this, maybe you don't. I look for easier ways to look at this. So both these quantities have an M in it. So M quantity Vf minus Vi divided by delta T equals F. Let's plug in now because we have an M in our givens. We have a Vf, we have a Vi, we have a delta T. F is what we're trying to solve for. So it makes sense that the given variables that you have written down match the line that you're actually going to put numbers into. You can successfully say, I totally get this. Look, Miss Arter, I understand that I have all the givens and the unknown that you were asking us to solve for and look at in this problem. So plugging in here, this should give us 1400 times 0 minus a negative 15 all over 0.30. Please include your calculated answer, guys. So your calculated answer here is 70,000. So that would give us a final force of, well, how many sig figs? You got 2 here, 2 here, 0 here, 2 here. Leading zeros never ever, lagging only with a decimal. So 2 sig figs is your final answer. 0 is obviously not going to round that up. So 7.0 times 10 to the 4th newtons? No! It's not that. You are in IB. You need to use the standard units here, not the derived units. So it should be kilograms meters per second squared. Box your final answer. On to the next one. Okay? Fantastic, guys. Okay, so furthermore, are you moving westward or are you moving eastward? Based off your final answer and the force that's applied here. Yeah, it's going eastward. How do you know that? Because your final answer came out in the positive direction. Very cool, very cool, very cool. Okay, so that's it on this video. The next one we're going to go to is on your stopping distances. So this video pretty much just looked at the impulse momentum theorem, talking about force, time, and impulse and momentum as the main key variables here. Please accomplish the worksheet now that coincides with this video on the impulse momentum theorem. Great job, guys.